All right. Thanks to the organizers for inviting me to this school. It's a great honor to teach here, and I'm very happy to have a very informal discussion of the topics. Students, please interrupt me at any moment. My name is Maxim. I do particle phenomenology, sometimes double down in cosmology and Big Bang nucleosynthesis. So I'm since some time now interested in physics of light beyond Standard Model weakly coupled states. So this is an enormous topic, of course, and I'm going to pick and choose in my lectures what to discuss. So we know from cosmology course and from popular literature that the energy balance of the universe is split almost entirely between dark energy and dark matter, and the atoms are only 5 or so percent from the total energy balance, and this is a substance that dark energy that doesn't cluster stays constant throughout the history as far as we have checked. Dark matter, on the other hand, could have some relation to particle physics. Maybe it's new particles, new light fields, and maybe there are actually new forces of nature associated. That come together with dark matter. So these are all question marks. So let's think very. So this topic has been sort of revitalized in the recent few years when people realized that. In particular, dark matter phenomenology gets a lot more exciting as you add light mediator forces, right? And in the past few years, there emerged some sort of a unifying view on the topic. It goes under the name portals. But before I get to that, let me have further kind of words of introduction. So let's think about forces in nature. So let's put a potential for a force with and most of the forces we know are of this form. So this is some sort of the coupling constant divided by r minus r over the range of the force, or if I go right away to particle physics, the mediator mass of a particle that mediates the force. It's the Yukawa interaction that we all know and love. And if I Fourier it, I get to the amplitude, which is alpha x. And since I'm writing, it seems in 3D, it's q squared plus the mediator mass squared. So now let's set up the stage and kind of plot very broadly what we know about the masses and mediators of forces, right? So here I would put the logarithm of the mediator mass, and here is the logarithm of the coupling constant alpha x. And in the Standard Model, we have forces from strong to weak to electromagnetic, sort of living in this domain from on this axis from 0 to, say, -2. And that goes from sort of massless mediators such as photons to maybe 1 GeV, where the roughly you can think of strong forces residing, and all the way to the weak scale, right? I furthermore can draw some sort of diagonal over here that would correspond roughly to the G Fermi, which is 10⁻⁵ over mp squared roughly, and this is a line where I equate alpha x over mx squared to G Fermi. Okay, so it's very naively you can say that this is the kind of standard model backyard, and this is unknown territory. All right, so of course the subject of this school and the subject of particle physics in recent years, as a matter of fact, or in some decades now, is to find the breakdown of the Standard Model, or to find the way how the Standard Model may be merging into higher frameworks. And for that, physicists develop tools, and of course the most precious tool we have is the Large Hadronic Collider right now. So it's best suited, not exclusively suited, but best suited for studying things that are relatively strongly coupled, well, the Standard Model type couplings, and with large masses, right? So this is LHC, or energy frontier direction. So with a few, well, in the last few years, you can say that there were significant inroads made along this direction, right? If you take, say, for example, an existence of new force mediated maybe by some Z prime particle, you know that LHC, for example, excludes or limits the particles that would look like the Standard Model Z bosons or W bosons, all the way to the 3 TeV mark, and the sensitivity is supposed to grow, right? So this is 1,000 times, or if you translate it into this variable, this would be 10 to the -3 of G Fermi. So it's really probing the milliweak strength couplings. However, if you think of some say particles that live along this line somewhere here, right, with much smaller couplings and with let's say not so large masses, right? The LHC would have a difficult time getting it, because the cross sections will not grow with energy, right? And they will turn around, fall down, and this would be a small particle on top of the huge QCD backgrounds, and small because of the small coupling constant. So therefore, there is, in principle, an alternative direction that is being discussed more and more, and that is intensity frontier direction. Okay, so to explore this energy frontier, you need particles colliding at larger and larger momentum transfers and or energies, and to get to this direction, you may not necessarily need LHC type energies, but you need a lot of intensity. So that's obviously a very important direction, and much of the US or North American sort of in-house particle physics activity is now sort of reoriented to neutrinos, to high intensity as Fermilab becomes an intensity frontier flagship. Questions? It's all very introductory. Now, maybe I'll just say a few, just to cheer you up, historically, how often do we come across a new fundamental force? So, of course, we probably should start from late 1600 with Newton and gravity, right? Then there is you'll see some pattern now. Now, in say 1960s, you can say that Maxwell have formulated E&M theory and showed the 1860, thank you, and showed the equivalence of light and electromagnetic waves, and then basically 1896-ish, there was a discovery of radioactivity, which is, in hindsight, you can say charge currents. Okay, and then sort of 1930s or mid 1930s, discovery of neutron and strong force that keeps together neutrons and protons. Then 1972 or so, there was a discovery of neutral currents, and that is Z exchange, if you like, in neutrino scattering. And that's how things are spaced, and then you can sort of, so 74 probably. And you can add another discovery here in 2012. Of course, this is a discovery of the Higgs boson, but so so far as what we know, it's consistent with being a completely elementary scalar, right? Which means a new force of nature and a new Yukawa force, right? Which is rarely advertised in popular talks, but it should be put here as a big deal, right? Yukawa force, Higgs mediated. So, in this latest kind of history, the delta T between the discoveries is like 38 years. So, if you add the 38 to 2012, you get maybe the prediction for the discovery of yet another force of nature. But so it's your job to work hard so that this will come not at the end of your career, but at the beginning. Okay. So that's these are very introductory words. So now let's set up some framework of how we're going to talk about the dark forces. Okay. Or dark sectors in general. So let me call it portal framework. I don't know why people chose this word, but anyways, so let's consider a theory that is composed of the Stern model plus some light and mostly neutral states that we'll specify in a moment, plus L interaction, right? So if we do, between the two sectors, if you don't know anything about if you don't have a very clear idea what you're looking for, you should start always from sort of writing down everything that's possible, right? That's consistent, and the framework that people choose, of course, is effective field theory framework, where you write down the sort of the standard model operators of canonical dimension n, and new physics operators of canonical dimension m. So this is the operators composed from the standard model fields, like, for example, G mu squared or psi d slash psi, etc., not necessarily scalars. And this is new physics that can come from, we'll discuss in a second what this thing is. And just by dimensional grounds, this is normalized on some energy scale n plus m minus 4. So let's specify whom are we going to look for in this new physics among the new physics states. So let's look at the light scalars. Light pseudoscalars, vectors, and fermions, neutral light states. So probably we'll call S singlet scalar, N neutral fermion, and so, for example, the so-called right-handed neutrino. Although right-handed is somewhat of a misnomer, because a conjugate state would be left-handed. And V mu, or sometimes people call it A mu prime, dark vectors. And specifically, a lot is discussed about the dark photons. These are massive particles with quantum numbers of the standard model photons and interacting with electromagnetic field currents. And so the mass range that I'm going to be interested. Well, I'm interested in all mass ranges, but for this topic of this mini series, they asked me to do the light states. So the mass range is from 0 to a few GeV. All right, so let's write down possible couplings to the standard model of this light states, starting from the operators of lowest dimension, because if there is a large scale lambda suppressing high dimensional operators, we should first enumerate interactions that are
singlet just means singlet under standard model.
Singlet under standard model under standard model gauge group. This is not. I mean, this is it's a framework, right? It's not a theory. You can add many things here. But let's first sort of finish this discussion of what's possible. So let's first form the standard model operators that are total singlets under standard model gauge group. That is, we apply gauge transformations to these operators, they stay the same. But I do not require them to be, at this point, total Lorentz scalars, so that I could have different possibilities of coupling it to different spins of particles, or different composite operators, and sticking it to the Lagrangian, right? So what do we have? So what's the lowest dimension operators that in the standard model that you can compose? Say it again. H squared, right? So H dagger H. Any other? F mu nu. Let's call it B mu nu for a moment. So this is the U1 hypercharge field strength. Okay. By the way, I'm using the standard model lingo, assuming that you guys are already have some expertise or some exposure to that, right? It's okay, I hope. So that's it. U1 standard model, U1 field strength. What else can we write down? HL, right? HL, right? Yes. So we'll write LH. This is this is dimension 2, right? This is dimension 2. This is dimension 5/2. Composite operator that is Higgs field here, and this is the left-handed doublet, right? So this is all good. At dimension 3, what can we do?
Psi bar psi.
That's psi bar psi is not going to work, because the left-handed and right-handed are charged differently, right? So if we insert gamma mu in between psi bar psi's, right, then we get, in principle, psi bar gamma mu psi. And here I could choose quarks, leptons, the right-handed quarks, right-handed leptons. So all these glorious representations of the standard model. Okay, in principle, right? So these are all currents, if you like, generalized currents that are going to be invariant under the standard model gauge transformations. Now, having formulated this sort of new players in the game, I can choose them and couple to this currents, right? So that is not necessary, because all these fields come in the chiral representation. So gamma 5 you can reabsorb again into the so if you want really psi, gamma mu, gamma 5 psi for an electron, you got to take L current and ER current, and with an opposite sign. That will give you the axial vector coupling to electrons. What's that?
Raise the board.
The raise the board. Is this? I can. What up to which point do you see? Up to here? I can just make it a little bit more compact. And then we have all this psi, gamma, mu, psi dimension 3 operators composed from these fields. All right, so let's now formulate the Higgs portal coupling. That is probably H star the D mu H, right? Very good. Yes. So let's sort of define the Higgs portal operator is when we take this H dagger H and couple it to the scalars, right? At the lowest dimension level, I can just put one scalar and put coefficient A in front of it. This is a unique operator in the Stern model or in this type of extensions because it defines a super-normalizable portal. That is, usually we're in the situation where the energy scales come in the denominator. This is the only one where you can write down where the energy scale comes in the numerator. And if you follow much of the recent phenol literature, there is quite an activity related to the so-called relaxion story, right? That's where you can choose this A parameter very small, then the mass of the S particle is not much renormalized by the loops other than by terms proportional to A squared. And so if you have a mechanism of scanning this this S parameter, you scan the Higgs mass. Okay, so it's azide, and then of course you can add a new interaction like this. Then if you have a new scalar charged under something, then you can use that instead of this, because this would violate symmetries. Now, if you have any U1 field, this is called kinetic mixing portal. If you have any U1 field, you can couple it to the this P mu coupling times F mu, and the coefficient in front people call epsilon. So this is new U1 field strength. All right. To obviously LH coupling, we can couple a neutral fermion, and that will define a neutrino portal. So LHN is dimension 4 operator equivalent to Yukawa interactions of neutrinos if we identify N with the right-handed neutrino. Now, in principle, I can take all this. Let's continue over here.
There is no lower one.
That's as fixed, right? All right, so I could possibly cover these things, and for dimension, for the various currents that I have here, well, I in principle can mix them with different coefficients and couple it to a new vector field V mu here, like this. This is a possible venue, but it's can be a dangerous exercise. Dangerous in what sense? That's right. That's right. So when you play with the vector particles, if you couple them to the conserved anomaly-free currents, then you guarantee that your theory can be UV complete to the high energy scales. So if not careful with anomalies, new strong interactions in principle. If you don't complete it, UV complete it in anomaly-free way, you will encounter new strong interactions. With so if I write it in this form and there is an anomaly, then there would be a scale of a new strong interactions set by the inverse power of this C1. So let me think for a second where it's going to be. So this scale of the new strong, new anomaly-induced interaction energy scale would be proportional to the mass of the vector over. No, I'd have to return it tomorrow to give you an exact account for what happens, but I have to move on. So there is a bunch of gauge symmetries here, however, that can be. There is a subset. There is a subset of currents. Completely free from anomalies. And these notably include B minus L, L mu minus L tau, or these are examples, and so you can take also linear combinations of this currents. Then they will be anomaly free, B minus 3 L mu, etc. All right. So then finally, yes. No. Any. You can. You may have to be very creative with how you arrange the mass matrices for neutrinos, but as at the level of currents, any of that is good. Yeah. That's right. Absolutely. So B minus 3 Li, let's say, and then you can take any linear combinations of those and cover everything in principle. So there are some sometimes you can find also a very non-trivial combinations between the lepton and the quark currents with different sort of pick and choose generations and charge assignments that to me look miraculously anomaly free, but you postpone usually your problems to constructing the mass matrices, right? So where these things are going to get difficult is when you start constructing mass matrices and develop the various what's called the flavor changing neutral currents out of these light particles. But we'll get to that. So for the axion portal, and I'm going to discuss it more today, in principle, you can take any vector current with left-handed fermion, for example, and couple it to the axion field like that. There is a gamma 5 inside here in the projector because L is left-handed. You can take G mu A, A over Fa and couple it to, for example, B mu nu squared, or B mu nu dual, then W mu nu dual, or G mu nu dual, where this is the SU3 field strength. This plays a very special role in the axion physics. Okay, so we have set up the framework in which we can study this these extensions of the Stern model. But before, so these things can happen, right? So, but before we discuss things that can happen, we should discuss the things we think they should happen, right? So that is, how is it motivated other than it can be, right? I mean, so that's a very important topic, and for me, on this list, the most motivated particles that you can add to the Stern model is the number 1 is the right-handed neutrino, and the number 2 is I didn't write it here. A axion. QCD axion. Let's put it this way. All right. You have listened or are about to listen to a series of lectures by Andrea on neutrino physics, right? So therefore, my coverage of the right-handed neutrinos will be cursory because I would imagine that he has covered this stuff. Well, then yes.
So the reason you said why right-handed neutrino or most plausible option is because
it's my own opinion, right? I mean, that you don't have to put down as you know the maybe you have so much conviction that dark photon is the most interesting particle, right? I think there is a very generic arguments why right-handed neutrinos is a welcome extension of the Stern model, right? And there is also a very strong argument to which I hope to get towards the end of this lecture why the axions are something that we should pay attention to and care about. All right. Yes.
Write down other operators like axion coupling to instead of the lepton current to H stack
Yes, you can do that. Yes. You can in principle do that. Yes. So you can couple this derivative structure to the anything that with the quarks or with H, right? Yes. Well, one thing that you should be careful when we talk about the QCD axion, you should not couple it with an arbitrary strength to say something like well, I don't know. Q. Okay, we'll discuss axions. So I'll get to that. All right. So maybe an aside about right-handed neutrinos. they're often also called neutral heavy leptons. By the way, this is a new object in the star that we introduced to the star model. So in principle, it's quantum numbers, and how we assign them are completely arbitrary, up to us. I can say, well, this is not a neutrino. This is a new state n that I couple that way to the star model. It carries no lepton number. Then the Yukawa interaction will violate the lepton number by 1 unit, and the Majorana mass will conserve it, right? Of course. Very well. So to the star model, we add delta L, which contains basically a new state which has an interaction with LHN through the Yukawa coupling, and in principle, I should let me choose my freedom for the charge assignments of the Higgs. Let me do this, and then so this is the interactions you can write down, and in principle you can have a mass term that doesn't violate any symmetries. That is probably complex conjugate, the mass term for the right-handed neutrino. So the neat thing about it, of course, as many of you know, is that if mn is chosen to be 0, then we have Dirac mass for the active neutrinos that is proportional to the wave of the star model Higgs, or equal in this particular Lagrangian to the wave of the star model Higgs times the Yukawa coupling, where this wave has a scale of 246 GeV. Now, I can, in principle, take this Mn and make it large, large compared to standard model scales, and that gives me a possibility to freely integrate out n from the spectrum, which from the point of view Feynman diagrams would be LH kind of diagram with n in between, where the n experiences the mass flip on the neutrino mass here, and the end result would be effective operator, that is 1 over Mn times the Yukawa coupling squared times what we have written LH plus complex conjugate. All right. So this once H goes to the vacuum condensate, then we have the mass of the light neutrinos scaling as Yukawa coupling squared, wave squared over 2Mn. So this is a framework sometimes called the Seesaw Mechanism, and of course the more kind of elegant way or agnostic way of accounting for neutrino masses in the star model would be to first just take this operator, high dimensional operator, and put it inside the star model, as an extension based on the fields that we know already, right? And that by itself would give all the phenomenology related to the neutrino masses and oscillations. However, it's a higher dimensional operator that would point out that at some high energy scale we would run into the strong interaction regime due to this, and it would therefore need to be UV completed if we care about the UV completion to the high energy scale. So this operator has many UV completions in principle, and what I've shown you is the one that is probably the most economic, but it's not by far not the only UV completion of the neutrino masses, right? So right-handed neutrinos would immediately imply the mass mechanism for the active neutrino masses, but this statement is not invertible. Neutrino masses by itself do not imply the existence of right-handed neutrinos, but to me they strongly hint to that direction. Well, at least it's half of the literature on the neutrino mass phenomenology is dealing with models that use right-handed neutrinos. Yes.
So once you have a large neutrino do you actually absolutely need spectral effect electrons? Or in some complete model I can have a seesaw mechanism where I don't have a
That's right. So you can. That's what I said, right? So if you can. You can take Stair model and add there, right, this divided over some scale lambda, right? And this is ij, right? So in principle, there should be some matrix aij in the flavor space plus complex conjugate. As far as we know, all the neutrino phenomenology that we know now can be described in that language. However, if you consider sort of I guess self-interactions of these things that at some point you would get bad UV divergences out of these operators, which would imply the necessity to UV complete if you care about the physics at the very high scale lambdas. Right? So this has a variety of UV completions, and right-handed neutrino is, well, let's say the simplest example. Although this is admittedly not a strict criterion, right? So that looks simple to me. Yes?
Just to understand, just to make sure I understand the logic here. So at the beginning, what we wrote down was a series of effective operators, right?
That's right.
So by that, I was thinking that our goal is to write down effective theories instead of UV complete theories.
In principle, yes, that's always a safe bet to start from your effective theories, right? So on the blackboard over there, except for the axion case, everything, especially if I stick to the anomaly-free combinations, can be just considered to be UV complete, right? So in that sense, these theories are embeddable right away to higher structures, right? So this will describe well the phenomenology of the right-handed neutrinos, of normal neutrinos, but by itself requires UV completion if we care about the high energy scales. If we stay at the level of effective operators, we may stay with that.
So you only consider the logical operators?
And indeed, over here, I have listed mostly the operators that are at dimension 4 and lower dimension, which is automatically renormalizable. So. That's right. It can be a dark matter. So returning to this framework, right, with light particles and different couplings, right? So depending on what you like, you can have dark matter out of scalars. You can have dark matter out of dark photons, for example, even though they look unstable, and they may be unstable, but if they're light enough, they can be stable on the scales of the universe, okay, of the lifetime of the universe. For sure, people discuss the dark matter built out of the right-handed neutrinos. What else did we discuss? Axions, of course, it can be dark matter, right? So dark matter is actually any framework. This framework, any participant beyond Stern model in this framework can be made in the dark into the dark matter, or at least as with the dark photon, as Tracy will discuss with you a lot. Also can be also made an efficient communicator or mediator between the dark matter and the Stern model sector. Okay. So now I would like to say a few words about the axions, the strong CP problem. Why I think this is the second most motivated light particle here, right? Moreover, with right-handed neutrinos, we don't know exact scale where they can be sitting, right? They can be at 100 GeV or at the gut scale or very light, right? So we don't know. But with axion, at least for what we know, the axions that solve strong CP problem will have to be very light particles, neutral particles. So let's discuss now the strong CP problem and the axions. Any further questions you have? Yes.
What scale should A be? Is it a full parameter?
That is correct. That is that a little bit depends. It's a good question. So what scale for A can we envisage in this model, right? So we should recall that there would be this. It's a correction to the mass term, and in principle there is a potential that the whole potential that can depend on fourth power and so on. The question is what would be the natural choice for A? That depends on whether you adhere to a very restrictive framework of technical naturalness or not, right? So if in principle I could stick any A here, right? But there would be, and I'm thinking of S as a light particle, right? So S can split into a pair of scalars from the Higgs doublet, and or only wave can interact with an actual Higgs. Whichever way you look at it, there will be a correction to the mass of the scalar particle that will go as proportional to the A squared parameter, right? So if you would make this A parameter much larger than a physical mass of a scalar particle, that means that in the in the original Lagrangian, you would have tuned cancellation between m0 squared and a squared terms. Okay, so if you want to avoid this, you can take this the inverse of that, which is this, and then it's okay from the point of view of technical naturalness. Okay, so there is that's not a not an insignificant consideration when especially when you start putting in high dimensional operators, right? So that the technical naturalness, right? If you play with the light particles and you organize corrections to the mass scale of these light particles, you may receive too large a correction from the quantum theory at the high scales, right? So the examples that I have shown mostly the sort of technically natural. If you choose the parameters to be small, they stay small.
So this scalar can become Z2 symmetry, so we'll break the Z2 symmetry.
It will.
Like big and,
Yeah, it will break the two symmetry. Yeah. The question of technical naturalness is okay. It's not super pressing when we play with masses of light fields, say in the MEV to GeV regime. That's well, it depends where your cutoff is as well. However, there's a whole class of literature that plays with say scalar fields that are light on the cosmological scale, right? Or keep rolling, evolving, right? And then there is always an issue of how to make them or keep them light if they interact with the standard model fields, right? If they interact non-derivatively, that is, if the corrections to their masses to their Lagrangians generate the mass terms, right? So whenever you hear a talk about the interacting quintessence fields, if you follow the cosmology literature, so there is like a rolling field that mimics the dark energy, and if you put in a coupling to the standard model fields, there will be an additional issue of how to make this so light, because the Hubble scale rate is 10 minus 33 electron volts. So how to make it light at that scale, right? And so that's maybe in the last lecture I'll get to talk about super light fields and what it means. Okay. Yes. It could, yes, absolutely. However, it depends on its mass, right? So we can easily let's do that, right? I mean, so well, maybe it's since I'm at that, maybe it's safer for me to analyze the in the remaining 15 minutes the phenomenology of this model rather than going into this strong CP and axion and then break for until Wednesday. What do you think? All right, so we postpone then the strong CP and axions and UV completions of axions for Wednesday. All right. So let's have a look at this since. Since it's a unique portal to the standard model, right? The one that has the super renormalizable portal, right? And it comes handy in this real axion discussion, right? So this is the interaction that we have. So what assuming that MS is small, much smaller than say a Higgs wave, right? As the Higgs breaks, gets its neutral component gets its expectation value, H naught becomes this, and we can sort of work out the 2x2 scalar Lagrangian that will appear in this model. And so there is, of course, that's my whole Lagrangian, and that's the scalar part of the Stern model. So when things go to the condensate, of course we will get the standard story with the standard model Higgs. But what's interesting is, of course, the scalar part here, which will have. Now you have to help me with this calculation. So we're expanding this to the first order in H. That gives a bilinear coupling between H and S. So it basically is A V H S. That's a cross term that appears from there. So this leads to the mass matrix given by the S squared AV MH squared, which can be simply diagonalized by the rotation that is proportional to AV over MH squared. That's the mixing angle, right? So diagrammatically, if you think about the Stern model fermion, there is the S particle that whose propagator is mixed on the AV and goes to the virtual Higgs boson, which has here the coupling to the Stern model coupling over V, right? That's basically the diagram, so that tell you how this S particle couples to the Stern model fields. I'm assuming that AV is so that A is much smaller than V. Okay, so that this mixing parameter is small, and I can take it into account by perturbation theory. Excuse me, you have to repeat it. At some point, it may develop a wave, of course. Moreover, the loop corrections from H here, right, could generate a tadpole for S, which I can, in principle, reabsorb into the mass matrix, right? I can shift the beginning of S to S equals 0. Since I didn't charge S under any particular gauge group, it's okay, right? This is inconsistent with the S being charged. So now we can basically get the effective interaction between the S particle and the fermion here of the Stern model, and that's that this coupling will be given, of course, by the mass of the Stern model particle over the wave times the AV over MH squared, which, as we have called it, a theta parameter, right? Or that's the not the theta QCD, but theta mixing. So of course, integrating out this standard model fermions and also W bosons and so on will also couple S particle to the electromagnetism, etc. Well, the question was about the stability of this particle. We can sort of estimate what it will be for different mass range. And since we are dialing a huge mass range, we should not be surprised to see a huge range of decay lifetimes. We can ask the question, and let me also take a prior on A proportional to ms, the one that saturates this naturalness bound. Then we can ask the question, how light S should be so that, say, it lives longer than the lifetime of the universe, or how heavy should it be so that if produced in the collisions, it decays within a reasonable framework to the detector, right? If we don't finish it, you gotta do it at home. Okay. All right, so that is the Higgs invisible decay will proceed especially happily if there is a S squared term and a lambda, and because then Higgs can decay to a pair of these particles. So lambda would have to be less than the Yukawa coupling of the B quark, otherwise the Higgs decay width would be saturated by the decays to the singlets. This, by the way, was a big point some 10, 15, 20 years ago, because at some point people thought that, well, including myself, maybe this S squared can be the dark matter itself through the sort of WIMP through the Higgs portal, if you like. And if it would be below mh/2, then the Higgs could decay. And moreover, if you actually choose this particle to be like 30 GeV or something and ensure the freeze-out abundance, then the Higgs does decay to this 90% of the time. So this model was immediately falsified once the Higgs decay was discovered to be in agreement with the standard model within 20 or 30%. All right. So let's estimate first the. So I'll just keep this. Since I did ms, right? So my effective Lagrangian then becomes S times psi bar psi times m for phi, and then here I would put ms vev over m Higgs squared. And a nice thing about it is that there is no guessing about the denominator these days, right? All right. So we can calculate the decay width, for example, for to 2 electrons. If say scalar is in the between the, say, the 200 MeV and 1 MeV, it will decay to 2 electrons, and we can calculate this decay rate. It's going to be 1/8 pi the mass of the scalar times the square of this coefficient. So it's m of electron over v squared ms v over m Higgs squared. All right. So. Very good. Very good.
You have to raise the middle first. Raise the middle.
Just raise this first.
This one?
Yeah, raise to the end.
All the way.
All the way. And then you can lower the.
Good. Clever. Now, now let's take then this gamma and calculate it to be 1 over 8 pi. Let's normalize ms on 10 MeV, because that's what typical scales in this intensity frontier experiments people look at. Then it's 0.5 MeV over the waves cancel, right? So let me first write down the final formula, right? I have ms to the fifth, no, ms cubed me squared over mh to the fourth, right? There you go. So we got to calculate that quickly because I'm running out of time. So 0.5 MeV over 125 GeV squared, and then let me take ms over 10 MeV cube, and then I have 10 MeV. That's right. Then I have 10 MeV cube. Yeah, and I have 125 GeV squared. There you go. No, that's good. Right. So, all right. So what do we get? 1 over 8 pi. This is going to be MeV over GeV gives me 10 minus 6. Then another 10 minus 6, and I have 0. And I have 5 over 125 squared. Here I have 10 over 125. So this is, let me be more smart. Let me take 12 MeV. So I can do that, right? So yeah, then I have MeV to GeV. So I have 12 MeV separately I should be writing. Then MeV to GeV gives me 10 minus 6. And then I'll have another 10 minus 2 from here. That that's right. So this ratio is 10 minus 4. And, very good. So we get to the roughly the answer. So we have 25 over 5, 8 pi, 10 to the minus 12 times 10 to the minus 8. So this is 10 to the minus 20 times 12 MeV. So which is 10 to the 7 electron volts, right? So it's and times, of course, this whole factor, the scaling. So that gives us the rate with which such particle would decay. It will decay at the rate of 10 to the minus 14 electron volts, right? And this is roughly, this factor is 1 over 1/5 or something like that, or 1/5. So this if I haven't made any mistakes, this would correspond to the lifetime of basically So I can write it as 2 times 10 to the minus 15 electron volts. So this becomes 3 hertz, which is 0.3 seconds. So this such particle, if it's not boosted very much, would travel 10 to the 10 centimeters before decaying. Okay, so the c tau for such particle would be on the scale of the 10 to the 10 centimeters, which is 10 to the 5 kilometers. All right, so this would correspond to the distances much larger than the detector, right? So if you are to explore such particles at the intensity frontier, you have to produce lots of them, so that only that some small fraction will decay within the volume of your detector. Right? Now we can sort of exploit this scaling, or you can do it at home, and lower MS to the. Of course, it will stop decaying to electrons. You have to go through another layer and calculate the couplings to the photons, and calculate at what level does this particle will have to, what mass it should be, so that it lives longer than the lifetime of the universe. If it can, there will be some additional constraints on from the gamma ray backgrounds that it will create, right? While decaying, and if you lower it ever still, then that it will stop producing any dangerous gamma backgrounds, and you can make it into the dark matter, no problem. Okay. So all right, so it was a very introductory lecture. Wednesday we'll continue with strong CP axions, axion-like particles. No?
We'll wash the board.
Okay.
Just go ahead and get the mic.
About this normally issue. So now we are out of